Welcome back to the deep dive. Usually, when we sit down at these microphones, we're dissecting, a specific news story or maybe a trending topic that's been blowing up everyone's feeds.
Mm.
But today, today is a little different. I've got a stack of papers on my desk that looks less like a news report and more like, well, like someone printed out the entire back-end code for Civilization, Earth Edition.
It really does look like that. And I think if you showed this stack to a casual observer, they'd see encyclopedia entries. They'd see Biology 101 or, Intro to Physics.
Right.
But the reason I'm so excited about this set of sources is that it's not theoretical. We aren't doing a history lesson today.
No, we're digging into the invisible machinery, the stuff that keeps us alive, fed, watered, and powered every single day, but that we completely totally ignore. I mean, I walked past a street lamp, ate a piece of toast, and drank a glass of water this morning, and I didn't think for 1 second about the physics or chemistry of any of it.
Which is how it should be, honestly. If you had to think about the complex fluid dynamics required to get water out of your tap every time you were thirsty, you'd never get anything done.
That's a good point.
But today we are going to look under the hood. We're exploring what the sources all point to as applied science.
Applied science. I like that. That's our theme.
Okay.
It's the difference between knowing E equals mc squared and actually building a nuclear reactor that lights up a city.
Exactly. It's science with dirty hands. It's science that has to solve a problem right now in the real world.
So here is the roadmap for you, the listener. We've broken this massive stack of research into 4 main pillars. We're going to start with the future of farming, which is way, way crazier than just planting seeds in the ground. We're talking robots, genetic editing, and farming in space.
Then we're moving to what I'm calling the microscopic chef. This is all about how we've, basically enslaved billions of tiny organisms to cook our food for us.
Enslaved is a strong word, but I think it's accurate. Then we've got water hacking, some really ingenious ways humans are harvesting water from thin air and even from ice.
And finally, powering the planet, the grid, the atom, and the sun. It's a full tour of the infrastructure of life itself.
Let's start with the most fundamental thing, food, and specifically the dirt it grows in, or soil. I feel like I should call it soil out of respect.
Soil is definitely the preferred term. And it's interesting because we tend to think of soil as just a physical thing,
Yeah.
a sponge that holds water and roots.
Yeah, just ground stuff.
But the sources really highlight that soil is actually a wildly complex chemical laboratory.
This was the first aha moment for me in the reading. The whole thing about pH level. I remember pH from high school chemistry, the litmus papers turning red or blue.
Right.
But I didn't realize how aggressive the chemistry of dirt actually is, or how much it matters.
It's the single most important metric for a farmer. So, just a quick refresher for everyone. The pH scale runs from 0 to 14. 7 is neutral, like pure water. Below 7 is acidic, think lemon juice or, battery acid at the extreme end. And above 7 is alkaline like bleach or ammonia.
And plants are picky, like really picky.
Incredibly picky. Most crops need a Goldilocks zone, usually right around neutral, maybe just slightly acidic, like between 6 and 7. But here's the part that usually gets glossed over in school. Why are you going to brain? Why does a plant care if the dirt is acidic?
Yeah, that's what I wanted to ask. It's not like the plant gets heartburn or something. Is the acid burning the roots?
Not exactly. It's all about solubility and what scientists call nutrient lockout.
Lockout.
Yeah. So soil contains all these great nutrients, nitrogen, phosphorus, potassium, the big ones. But plants can't just, bite a chunk of potassium. They need it dissolved in water as ions so they can suck it up through their roots.
Okay, so the food has to be in liquid form.
Yeah.
Got it.
Correct. Now, imagine the soil is too acidic. On a chemical level, that just means there's a high concentration of hydrogen ions floating around. And these hydrogen ions are, they're aggressive.
Okay.
They react with the nutrients and with the soil particles themselves, and they effectively bond everything together. They turn the available dissolved nutrients into solid, insoluble compounds.
So the food is right there, but it's basically glued to the dirt.
Precisely. You could dump a literal ton of fertilizer on a field, but if the pH is too low, the plant roots will starve to death while sitting on a mountain of food. The chemical door is locked.
That puts a whole new spin on farming. It's not just watering and waiting. It's like you're managing a chemical equilibrium constantly.
You are a chemist first and a farmer second.
And the sources mention that even rain makes this harder.
It does. Rainwater isn't perfectly neutral. As rain falls through the atmosphere, it grabs carbon dioxide from the air, and that forms a very weak carbonic acid.
Huh.
Now, over millions of years, this is the process that dissolves limestone to create huge caves. But on a farm, over just a few seasons, it slowly but surely pushes your soil toward acidity.
So the default state of a farm in a lot of places is to slowly drift toward being unusable.
In many climates, yes, which is why farmers have to play chemist. They use something called agricultural lime. It's basically just crushed limestone calcium carbonate. It's alkaline.
And they just spread it on the
You
field.
spread it on the fields, it reacts with the acid in the soil, neutralizes those aggressive hydrogen ions, and unlocks the nutrients again.
It's a giant Tums for the earth.
That is a chemically perfect analogy, yes.
Now, there was one specific example of this soil chemistry that I found absolutely fascinating because I've seen it my whole life and never understood it. The hydrangea flower.
The natural litmus test. It's so cool.
I always just assumed there were two species of hydrangea, the blue ones and the pink ones. But the source says it's the same plant.
It is the exact same plant.
Right.
The color isn't determined by its genes alone, it's determined by the soil chemistry it's sitting in. But the mechanism is the really cool part. It's actually about aluminum.
Aluminum, like
Yep.
from a soda can.
Yes, the metal. Aluminum is naturally present in most soil, but usually it's all locked up and insoluble so plants can't access it.
Ah, so it's locked out, just like the other nutrients.
Exactly. But when the soil becomes acidic, that aluminum suddenly dissolves and becomes available for the plant to absorb.
Okay.
The hydrangea roots suck up this newly available aluminum, and the aluminum ions travel up to the flower petals and bind with the pigment molecules, and that interaction turns the flowers blue.
So a blue flower literally means acidic soil.
It does. And if the soil is neutral or alkaline, the aluminum stays locked in the dirt. The plant can't get to it, so the flowers just stay their default color, which is pink.
That is wild. You can literally diagnose the chemical health of your garden just by looking at the color of the petals.
It's a biological dashboard. It's amazing.
Okay, so that's traditional dirt farming. But then the sources take this hard left turn where it's seeing a massive shift where we just ditch the soil entirely. Hydroponics and aquaponics.
This is where we move from managing nature to really engineering nature. Hydroponics is at its core just growing plants with their roots suspended in nutrient-rich water. No dirt involved at all.
The headline stat here, the one that really jumped out, is the water usage. The source says hydroponics uses up to 90% less water than regular farming,
Right.
which honestly broke my brain for a second. The plants are sitting in water. How on earth does that use less water?
It's so intuitive once you think about where all the water goes in a traditional field.
Yeah.
You spray a field with thousands and thousands of gallons. Some of it evaporates into the air immediately.
Yeah.
Some of it drains deep down into the water table where the plant roots can't even reach it. Some of it just runs off into rivers. It's an incredibly wasteful system when you look at it closely.
It's a leaky bucket, a giant leaky bucket.
Exactly. Hydroponics, on the other hand, is a closed loop. The water circulates past the roots, the plant drinks exactly what it needs, and every drop of the rest goes right back to the tank to go around again. We catch and reuse everything.
But there's a big engineering challenge here, right?
Yeah.
You can't just stick a plant in a cup of water and call it a day. I've tried that with houseplants. The roots just rot.
They drown, and that's the key. Roots need to breathe. They need oxygen just as much as they need water nutrients. If you just submerge them in a bucket of stagnant water, they suffocate and die.
So how do you solve that?
You have to actively oxygenate the water. So you'll use things like air stones, like in a fish tank, to bubble air through it. Or you'll have pumps, or even systems that are designed to drain and flood the roots on a cycle so they get a chance to breathe air directly.
The source mentioned that rotating farm in Japan.
Oh, the one in Rikuzentakata. Yeah, that's an amazing example. It's this giant circular rotating system where the lettuce slowly moves in a spiral for 30 days, getting exactly the right amount of light and nutrients until it reaches the end of the line ready for harvest.
It's like an assembly line for salad.
It is. And then there's aquaponics. This is one that really feels like magic to me. You combine the whole hydroponics setup with a fish tank.
It's biomimicry, right? You're basically recreating a tiny, perfect pond ecosystem.
That's the goal.
So explain the cycle, because the simple version everyone hears is fish poop feeds plants. But there's a crucial missing step in there, isn't there?
There is a massive invisible missing step. And without it, the whole system dies. If you just took fish waste, which is mostly ammonia, and poured it on a plant, you'd kill the plant. Ammonia is toxic to plants, and it's also toxic to the fish if it builds up.
So how does it possibly work?
The secret ingredient is bacteria. You need a biofilter in the system, which is just a place for specific bacteria to live. There are two kinds, Nitrosomonas and Nitrobacter.
Okay.
The first group, Nitrosomonas, eats the toxic ammonia from the fish and converts it into something called nitrates. But nitrates are also still pretty toxic.
You're not done yet.
Not yet. Then the second group of bacteria, Nitrobacter, eats the nitrates and converts them into nitrates. Nitrates are the perfect plant food. They're exactly what plants want.
So the bacteria are the translators. They translate toxic fish poop into gourmet plant fertilizer.
Exactly. They are the indispensable middlemen. Without those invisible bacteria doing their work, the whole system just crashes. But when it works, it's beautiful. The fish feed the bacteria feed the plants, and the plants filter the water, leaving a clean tank for the fish.
It's a perfect circle. And speaking of perfecting farming, let's talk about the workforce, because we aren't just changing the soil, we're changing the farmer. Or maybe replacing the farmer. We're talking about robots.
Automation. But not just dumb automation like a sprinkler on a timer. We're talking about machine learning and AI.
The source highlighted a robot called Flippy, which is a burger flipping robot. And look, I get that flipping a burger is repetitive, but the strawberry picker, that seems almost impossible for a machine.
Why does it seem impossible to you? What's the main challenge?
Well, have you ever picked a strawberry?
Yeah.
They are so delicate. If you squeeze even a tiny bit too hard, it's just jam. If you pull too hard, you rip the whole plant. And they hide under the leaves. They're not just hanging there waiting for you.
That is the engineering nightmare in a nutshell. It's what's called an unstructured environment. In a car factory, the metal part is always in the exact same inch of space every single time.
Right.
In a strawberry field, the fruit is moving in the wind, it's partially hidden by leaves, the lighting changes constantly as clouds pass overhead. It's chaos.
So how does a robot possibly handle that chaos?
It starts with vision. The robot has cameras, but more importantly, it has a brain behind the cameras that can understand what it's seeing. Engineers train a neural network with thousands, maybe millions of photos of strawberries.
Every kind of strawberry imaginable.
Red ones, green ones, half-eaten ones in deep shadow, ones in bright sunlight. The robot learns the concept of ripe strawberry.
So it's not following a simple, if it's red, pick it command.
No, it's far more nuanced. It calculates a ripeness score based on deep color analysis. It identifies the precise location of the stem, and then comes the physical part. It doesn't use a metal claw, like in an arcade game.
That would be a disaster.
It would be a smoothie. It usually uses soft robotics, things like silicone grippers that gently inflate with air to cup the fruit, or specially designed little cups that can twist the fruit off the stem without ever crushing the cells.
The stat in the notes is just staggering. One robot can pick 794 pounds of strawberries in a single day. That's, what, 360 kilograms?
It's the work of a huge crew of human pickers. And the robot doesn't get back pain, it doesn't get sunburn, and it can work all night long using infrared cameras.
That is both terrifying and amazing at the same time. But let's go even deeper into the biology itself. Genetically modified foods. The source brings up two really different examples. The rainbow papaya and the purple tomato.
The rainbow papaya is a great starting point because it wasn't about making a superfood or making more money. It was a rescue mission. Pure and simple.
A rescue mission?
Yeah. In the 1990s, the ring spot virus was absolutely wiping out papaya plantations in Hawaii. It was a total devastation for the farmers. The industry was on the verge of collapse.
So this wasn't corporate greed. This was, we have to do this or we lose everything.
Exactly. Scientists took a tiny, harmless piece of the virus's own protein shell and inserted the gene for it into the papaya's DNA. It works almost like a vaccine for the plant.
How so?
The plant starts producing this harmless viral protein in its cells. And the presence of that protein makes the plant effectively immune to the actual dangerous virus. The virus can't take hold.
That's incredibly clever. It's like teaching the plant's immune system to recognize the enemy.
That's a great way to think about it. It saved the entire Hawaiian papaya industry.
The purple tomato, that one seems more cosmetic or maybe elective.
It looks cosmetic on the outside, but it's actually all about nutrition. They took a gene from a snapdragon flower, you know, the common garden flower.
Sure.
Snapdragon genes have the instruction manual for how to make something called anthocyanin. That's the deep purple antioxidant chemical you find in things like blueberries and blackberries.
Which everyone says are super healthy for you.
Right. They're powerful antioxidants. But tomatoes don't normally make them. By splicing in that Snapdragon instruction manual, scientists got the tomato plant to start pumping out anthocyanin.
It turns the tomato deep purple.
Deep purple, and it becomes a high antioxidant fruit. So you get the benefits of a tomato and the benefits of a blueberry all in one.
We're literally editing the source code of our salad.
We are. And of course, there are huge, valid debates about the ethics and long-term stability of this technology. But from a pure applied science perspective, it's undeniably impressive to be able to cut and paste traits between a flower and a fruit.
Okay, last stop on the farming tour. We're leaving Earth entirely. Space plants. The ISS.
The ultimate hostile environment for a farmer.
I always assumed the biggest problem with space farming would be like radiation or maybe getting enough light, but the source focuses on water.
Water behaves very, very strangely in microgravity. On Earth, if you pour water on soil in a pot, gravity is the dominant force. It pulls the water down and out through the lateral.
Drainage.
In space, there is no down. There's no gravity to pull the water through.
So what happens? What's the dominant force then?
Surface tension. Water wants to stick to itself.
Mm.
It wants to stick to surfaces. So if you just had a pot of dirt and you tried to water it, the water might just ball up and float away.
That seems bad.
Or worse, it might cling to the plant roots so tightly that it forms a film of water around them and literally drowns them. It won't drain away.
So you get fluid physics problems instead of what you think of as farming problems.
Exactly. The solution they developed involves these specialized root pouches or pillows. They use a clay-like material that wicks water evenly through capillary action, ensuring the roots get constant, gentle moisture without being drowned or having the water float off into the ventilation system.
And they've actually grown food and eaten the results.
Oh, yeah? They ate red romaine lettuce back in 2015, and then in 2016, they grew zinnias. They were the first flowers to ever bloom in space.
Why flowers? That seems like a waste of resources when you could be growing calories. Why grow something you can't eat?
The source mentions the psychological aspect, which I think is fascinating. Scott Kelly, the astronaut, really took charge of the flowers. And there is something profoundly necessary for the human brain. When you are trapped in a metal can, surrounded by wires and beeping machines for a year, to see something organic and colorful and alive.
It's a connection to Earth.
It's mental health support. The flower isn't a calorie source, it's a sanity source.
I love that. And I guess if we ever want to go to Mars, that psychological connection to Earth-like biology will be absolutely crucial.
It will be non-negotiable.
All right, let's pivot. We've grown the food. Now we're going to talk about that microscopic, chef.
Fermentation.
This section really hit home for me because I love cheese, I love bread, I love chocolate, but I never really stopped to think about the fact that all of these things are basically slightly carefully rotted.
Controlled spoilage is the polite term.
Huh.
But yeah, that's what it is. We are outsourcing our cooking to an army of microbes.
So on a mechanical level, what is happening? When we say fermentation, what are the bugs actually doing?
It's metabolic. These microbes, we're talking bacteria, yeast, fungi, they're hungry. They're looking for energy, and their favorite food is usually sugar. They consume the sugar in the food, and as a waste product, they release other things.
Things we want.
Things we want. Things like acids, gases, or alcohol.
So we're essentially eating their leftovers.
We prize their leftovers. Let's look at cheese. Milk is basically sugar water. The sugar is called lactose, with some fat and protein floating in it. We add specific bacteria, they eat the lactose, and, well, they poop out lactic acid.
And it's the acid that does all the work.
The acid changes the pH of the milk. It causes the milk protein, specifically a protein called casein, to unravel from their normal shape and start clumping together. That's curdling.
Yeah.
The liquid turns into a solid.
And that solid is cheese.
That solid is the most basic form of cheese. But then you have the really interesting part, the aging process. The source mentions how French cheesemakers tap the wheels of cheese.
Yeah, that sounded like some kind of ancient ritual.
It's acoustics. It's applied physics. As the mold and bacteria inside the cheese continue to eat and digest the proteins and fats over months or years, the texture of the cheese changes. It goes from being chalky and firm to being soft and creamy.
And the sound changes.
The sound of the cap tells the cheesemaker about the density of the inside. They are literally listening to the microbes finishing their dinner. They can hear when it's ripe.
That is bizarrely poetic. I love that. Okay, bread. We all know yeast makes bread rise, but how? What's the actual mechanism?
Yeast is a type of fungus, a single-celled fungus. You mix it into the dough and it starts eating the starch and sugar in the flour. Its primary waste product is carbon dioxide gas, CO2.
The same stuff we breathe out.
Exactly the same stuff. Now, wheat flour has a special protein in it called gluten. And when you knead dough, you develop these gluten strands, and they are very elastic, kind of like a tiny balloon.
Okay.
The yeast produces CO2 gas, the gas gets trapped inside millions of these tiny gluten balloons, and the whole loaf of dough expands, it rises.
So the holes in my sourdough loaf are just trapped yeast farts.
Scientifically speaking, yes. And when you put the loaves in a hot oven, the heat sets the gluten, freezing all those bubbles in place. That's what gives bread its light, airy crumb.
Unbelievable. And chocolate. I had absolutely no idea chocolate was fermented. I thought you just, picked the cacao bean and ground it up.
If you did that, it would taste absolutely terrible. Raw cacao is incredibly bitter and astringent. It has none of the flavors we associate with chocolate.
So what do they do? How do you get from bitter bean to chocolate bar?
It's all in the fermentation. They take the wet, slimy beans right out of the pod, and they pile them up, usually under big banana leaves, and they just let them sit in the tropical heat for several days. They're deliberately letting them rot.
Wow.
The slimy pulp ferments first. The temperature inside that pile spikes. It gets really hot, up to 122 degrees Fahrenheit or 50 Celsius. This heat kills the germ of the seed so it can't sprout, and more importantly, it triggers a cascade of chemical reactions inside the bean that create the precursors to chocolate flavor.
So the flavor isn't there to begin with. It's created by the process.
It's created by the fermentation. Without that rotting phase, you could roast that bean all day long, and it would never, ever taste like a chocolate bar.
So the flavor of chocolate is actually a byproduct of the death of the seed during a controlled rot.
In a way, yes. It's pretty amazing.
I'm never looking at a Snickers bar the same way again. Okay, moving on to our third pillar, water hacking.
This is a critical one. The source notes that back in 2019, more than 780 million people lacked easy access to clean water. The problem is immense.
And the solutions here are what I love about engineering. It's not always some high-tech computer chip. Sometimes it's just really, really clever geometry, like the ice stupa.
In Ladakh, India, it's in the high Himalayas, and it's what's known as a cold desert. They get almost no rain, only about 2 to 3 inches a year. All their water comes from glacier melt.
And the glaciers are disappearing because of climate change.
Exactly. So they have water in the winter in the form of snow and ice, but it all melts and runs away in the spring before the farmers actually need it for planting in the summer. They needed a way to store winter water for summer use.
But building giant water tanks is expensive and difficult up there.
So they store it as ice, but here is the physics problem. If you just have a big frozen pond, the surface area is huge. The summer sun hits that flat surface and it melts way too fast. It's gone before you can use it.
So how does the stupa shape solve that?
It's a cone. In the winter, they run a pipe up from a stream and just spray the water into the freezing air like a fountain. It freezes as it falls, and over the winter, it builds up this massive cone of ice. Some of them are 70, 80 feet tall.
But why a cone? What's special about the shape?
Geometry. A tall, narrow cone has a relatively small surface area exposed to the direct sun compared to the massive volume of ice that's stored inside it. It's the same reason a crushed ice cube melts way faster than a solid block of ice.
Less surface area.
Much less surface area. So the stupa melts slowly, incredibly slowly. It just drips water gradually throughout the late spring and early summer, perfectly timing the release of water for when the farmers need to irrigate their fields.
It's a time-release water battery?
Built entirely out of temperature, gravity, and clever geometry.
Then there are the fog catchers. This feels like something straight out of the sci-fi novel Dune.
It's used in places like the mountains of Morocco, places that are technically deserts, but get heavy, dense fog rolling in from the ocean. Fog is just, a cloud full of water that's too light to fall as rain.
So how do you catch it?
With nets. Big mesh nets. But the design of the mesh is absolutely key. If the holes in the mesh are too tight, the wind just sees it as a solid wall and goes around it, taking the fog with it. If the holes are too loose, the fog just passes right through. It has to be that perfect in-between size to allow the wind to pass through, but to catch the water droplets.
And when the fog hits the mesh?
It's a process called coalescence. Tiny microscopic water droplets hit the fibers of the net and they stick. Then another droplet hits and merges with it, and another. Eventually, the drop gets heavy enough that gravity overcomes the force of the wind, and it slides down the net into a collection trough at the bottom.
The Cloudfisher model mentioned in the source can get 130 gallons a day.
On a good foggy day, yes, up to 600 liters, without a single volt of electricity. It's just passive collection from the air.
Now let's talk about something a bit less elegant, maybe Los Angeles. The shade balls. This is a viral photo a few years ago. A reservoir completely covered in millions of black plastic balls.
96 million of them, to be exact.
It looks like a ball pit for goth kids. It's a bizarre image. But there is some really serious chemistry and physics happening here.
The primary goal was simple. Stop evaporation. LA is hot and dry. Covering the surface of the water with these balls stops the wind and the sun from stealing it. They saved something like 300 million gallons of water a year just from that. But there was a second, more complicated chemical reason.
Yeah.
It has to do with something called bromate.
Bromate.
Yeah. So the reservoir water naturally contained a harmless chemical called bromide, with a D.
Okay.
And like all cities, Los Angeles treats its water with disinfectants, like ozone or chlorine, to kill bacteria. The problem is, when you mix bromide plus chlorine plus sunlight, you get a chemical reaction that creates bromate, with a T. And bromate is a suspected carcinogen.
So the sunlight was the catalyst for creating a toxic chemical in their drinking water.
Exactly. The balls are basically sunglasses for the reservoir. They're opaque. They block the UV radiation from the sun, which stops that chemical reaction from ever happening.
So why black? That seems counterintuitive if you want to stop heat and, keep the water cool. Shouldn't they be white to reflect the sun?
You would think so, but it's about longevity. White plastic breaks down really fast in intense UV light. It gets brittle, and it crumbles into microplastics.
And you don't want that in your water supply.
Definitely not. So they add a substance called carbon black to the polyethylene plastic. The black pigment absorbs the UV radiation and protects the plastic itself from degrading. Those black balls are designed to last for 25 years. If they were white, they'd be dust in just a few years, polluting the very water they were meant to save.
That's a fascinating, counterintuitive engineering choice. I love it. Okay, let's get to the final water topic, the gross one. Wastewater treatment.
The 144 million Olympic swimming pools of sewage produced in 2020 alone. It's a staggering amount.
We flush and we forget. But where does it all go?
It goes to a treatment plant, which is basically a giant factory designed to speed up nature's cleaning processes. The very first step is simple physics. Sedimentation.
Just letting it all settle.
Pretty much. You put the raw sewage into a large, quiet tank and you just wait. Gravity does the work. The heavy, solid waste, the sludge, sinks to the bottom. Later stuff like oils and grease, the scum, floats to the top.
And you just get rid of the top and bottom layers.
You scrape off the top and you pump out the bottom, and the water left in the middle is already significantly cleaner.
But the sludge? What on earth happens to the sludge?
We treat it, often using something called anaerobic digesters, which are basically big, heated, oxygen-free tanks full of our old friends, bacteria.
The microscopic chefs are back on the job.
They are. They eat all the pathogens and the organic matter in the sludge. What comes out at the end is a dried, solid material that's been given the very appetizing name sludge cake.
Sludge cake. Sounds delicious.
It's definitely not. But it's rich in nitrogen and phosphorus, so we use it as fertilizer on farms.
And there is the loop again. It keeps coming up. We eat the food, we produce waste, we process the waste to create fertilizer to grow more food.
It's the only way to live sustainably on a finite planet. You have to learn how to close the loop.
All right, let's power through to our final section, powering the planet. Let's start with the grid.
Probably the largest, most complex single machine that mankind has ever built.
That's a very big claim.
Think about it. It's a single interconnected web of copper and steel and transformers stretching across entire continents. And the craziest part about the grid, the thing that is so hard to wrap your head around, is that for the most part, it has no storage.
Wait, what do you mean no storage?
I mean that electricity, generally speaking, must be generated at the exact millisecond that it is consumed. When you flip a light switch in your house, a turbine at a power plant somewhere, maybe hundreds of miles away, has to work just a tiny bit harder to push those specific electrons to you right now.
That sounds incredibly fragile.
It is. It's a constant high-wire balancing act. And it's all about synchronization. In the U.S., the grid runs at a frequency of 60 hertz. That means the alternating current switches its direction back and forth 60 times every second.
Okay.
Every single generator connected to that grid, whether it's nuclear, coal, hydro, wind, every one of them has to spin in perfect lockstep at that exact frequency.
What happens if one of them spins too fast or too slow?
It breaks things. If the frequency drifts even a tiny fraction of a percent, sensitive equipment can damage itself, or automatic safety trips will fire, causing cascading blackouts. The grid operators are constantly, second by second, balancing generation with demand to keep that frequency stable.
And voltage is the pressure in the system.
Yes. Think of voltage like water pressure in a pipe. To get electricity from a power plant to a city hundreds of miles away, without losing most of it as heat in the wires, you need massive pressure. So we use step-up transformers to boost it to 400,000 volts or even more for that long-distance highway travel.
And then you have to step it way, way down so my toaster doesn't vaporize when I plug it in.
Exactly. A series of step-down transformers reduces it to the safe 120 or 240 volts you have in your house.
So where do all these electrons come from? Let's talk about the old guard, nuclear.
Nuclear fission. We've been doing this for decades. You take a big, heavy, unstable atom like uranium, you shoot a tiny particle, a neutron, at its nucleus. It becomes unstable and it splits apart.
And that split releases a huge amount of heat.
Massive heat. But here's the thing people often forget. At its heart, a nuclear power plant is just a very, very complicated steam engine. We use the most advanced nuclear physics known to man for one purpose.
To boil water?
To boil water, to create steam, to spin a turbine, to turn a generator.
That seems so Victorian. It's almost comical.
It works. But the big downside, of course, is that the process creates radioactive waste that stays dangerous for thousands of years. And that's why there is so much research and excitement around its alternative. Fusion.
The holy grail of energy.
Fusion is what the sun does. Instead of splitting heavy atoms apart, you're smashing light atoms, like types of hydrogen, together to make a heavier atom, like helium.
And why is that so much better?
Well, a few reasons. One, it releases far more energy per pound of fuel. Two, the fuel itself is basically derived from water, so it's incredibly abundant. And three, it produces no long-term, high-level radioactive waste.
So why don't we have it yet? It sounds perfect.
Because atoms really, really don't want to touch each other. The nuclei of atoms are positively charged. And just like two north poles of a magnet, they repel each other with incredible force.
Right.
To force them to fuse together, you need to recreate the conditions in the core of the sun. You need temperatures of over 100 million degrees Celsius and immense pressure. We are literally trying to build a box on Earth that can hold a piece of the sun. It is arguably the hardest engineering challenge in history.
Speaking of the sun, let's talk about solar power.
Our own personal fusion reactor in the sky, the stat in the sources is just mind-blowing. 1 single hour of sunlight hitting the surface of the Earth contains more energy than all of humanity uses in an entire year.
That is staggering. We are just bathed in a constant, overwhelming excess of energy.
We just have to get better at catching it.
Yeah.
And that's what photovoltaic solar panels do. They work on the quantum level. A particle of light, a photon, streams from the sun and hits a silicon cell in the panel. And that impact has just enough energy to knock an electron loose from a silicon atom. That loose, moving electron is the electric current.
There are no moving parts, no boiling water, no steam.
Just silent, solid-state physics.
But the sun sets and the wind stops blowing. Which brings us to the final critical piece of the whole puzzle. Storage. If the grid has to be balanced every second, how can we possibly rely on intermittent sources like solar and wind?
We need batteries, but not just the AA batteries in your remote. We need grid-scale energy storage.
Chemical batteries like the lithium-ion ones in electric cars are getting bigger and better.
They are, absolutely. But there are also these fascinating mechanical batteries, like flywheels.
Explain that. That sounds like something from a steampunk novel.
It kind of is.
Yeah.
You take a massive, heavy wheel, often made of carbon fiber, you put it in a vacuum chamber so there's no air resistance, and you use magnetic bearings so there's almost no friction.
Okay.
When you have excess solar power at noon, you use an electric motor to skin that heavy wheel up to insane speeds. We're talking tens of thousands of RPM.
So you turn the electricity into physical motion.
Into kinetic energy. That wheel will just keep spinning for a very long time because there's nothing to slow it down. Then, when you need power at 6 p.m. after the sun has gone down, you flip a switch and the motor becomes a generator. It puts a drag on the flywheel, slowing it down and sucking that momentum back out as electricity.
It's a spinning battery.
It's a spinning battery. And then there's pumped hydro. This is actually the biggest and most common form of grid-scale energy storage we currently have.
This involves hills and lakes, right?
2 reservoirs, one at the bottom of a hill and one at the top. When electricity is cheap and plentiful, say on a windy night or a sunny afternoon, you use that power to pump huge amounts of water from the lower lake, UP the hill, to the top lake.
So you're storing the energy as potential energy.
As gravitational potential energy. The water sitting up there is like a coiled spring,
Mm-hmm.
and then when you need the power back during peak demand, you just open the floodgates. The water rushes back down the hill through turbines and generates electricity. It's incredibly simple and very efficient. We're using gravity to store sunlight.
That is actually beautiful. It's so elegant.
It really is.
So we've covered a lot of ground today, from the H plus ions in the soil all the way to the gravitational potential energy of a lake on a hill. What's the big picture here? What did you take away from this whole deep dive?
For me, it's the realization that so much of applied science is just humanity learning to play by nature's rules instead of trying to bulldoze them. We used to just, chop down the forest, pave the earth, fight against nature. But the most advanced, most exciting tech we discussed today, aquaponics, fog catchers, solar, pumped hydro, it's all about observing how nature already works and then cleverly, gently, slipping our own machinery into that existing flow.
The loop concept really stuck with me. The idea that in all these advanced systems, there is no such thing as waste. There's only input for the next system. The fish poop feeds the plant. The sludge cake feeds the farm. The sunlight that hits the earth is captured to pump the water that will power the grid later.
We are finally, I think, learning to think in circles instead of just straight lines. And that is a very, very hopeful thing for the future.
So, to you, the listener, next time you see a hydrangea, check the color you're doing chemistry. Next time you eat a piece of bread, take a second and thank the fungus. And next time you flip a light switch, spare a thought for the grid operator somewhere trying to keep all the spinning plates of modern civilization from crashing down.
It's a quiet miracle that anything works at all, really.
On that comforting note, thanks for listening to the deep dive. We'll see you next time.